Dan wil ik nu Susan Deeny naar voren vragen. Susie, please join the floor. Susan werkt voor ARUP of ARUP. Het is het gerenommeerde ingenieursbureau uit de UK, maar verder dan de UK ook. En ze zal ons voornamelijk ook, laten we zeggen, inleiden in de fire safety engineering in de meer complexe structuren en eigenlijk de oplossingen die daarvoor gezocht en geboden worden. Thanks, Susan. The floor is yours.
Good start. Hello, once again. We'll start over. I don't know how many minutes I've just lost. So I'm a structural fire engineer by training. I did my PhD in structural fire at the University of Edinburgh. And I lead the structural fire engineering team at ARUP. And I was saying that structural fire is a particular kind of hobby horse, I guess, of ARUP's. We first did our very first structural fire engineering job actually 40 years ago. So when Margaret Law designed the external steel structure of the Pompidou Centre in Paris. And that was a very revolutionary design at that time. And since then, we've invested very heavily in structural fire engineering research. To date, we've sponsored over 13 PhDs, looking specifically at structural fire behaviour. And we also fund the Professor of Structures and Fire at the University of Edinburgh, so that's Professor Luke Bisbee. And why do we do this? Well, if fire safety engineering is a very young field, then structural fire engineering is really in its infancy. So if we want to drive it forward, then we need to have the knowledge to do that before we bring that into commercial design. And so that's ARUP's role. We commercially design structures and do performance-based design. So I think I'm not really going to talk about structural response too much today, but I think it's worth just giving a very brief overview. In the UK, really the Broadgate construction fire was, when we look back, quite a pivotal moment in the development of structural fire research. So it was a partially protected structure which was under construction, and there was a very severe construction fire. And the structure afterwards, it was a steel frame, concrete composite structure, actually exhibited very little damage. And what this sort of said to the steel industry is that there's actually a lot of inherent strength in a steel frame that we're not accounting for in our design. And so in a quite a forward-thinking way, they started to sponsor, along with government research, lots of research into actually how steel frames respond to fire. So not just beams and columns isolated in a furnace, but actually when we look at the structure as a whole, how does that respond to a fire? And that culminated in, and you might be familiar with the Cardington full-scale fire tests, which was a seven-story steel frame building, which they set alight, and use that to actually validate the numerical models and all of the design tools that we have for structural fire research. So when we're doing these very complex models, we've got confidence in them because we've actually done full-scale fire tests behind that to validate that behaviour. Now, less than a decade later, we realised that there are some really significant inherent weaknesses in the performance of steel structures in fire as well. And so it's very well with structural fire engineering research to talk about how much stronger things are in fire, but we also need to be mindful of how they can be weaker. And a lot of the forensic research done by NIST and other academic institutions really spelt out how vulnerable our tall buildings are if we've got a multi-story fire. And I think as Sean was saying earlier, the thing that stops us from having a multi-story fire is the fire stopping, the quality of our compartmentation construction. And so how much can we rely on that if we're talking about the stability of a tall building in a city centre location? So we need to be very sure. So there are some buildings that should just never collapse in fire. So when we're doing that design, that's something that we need to think about. And so the last 20 years has seen a huge amount of research in the very detailed analysis of steel structures, concrete also, and their response to fire. And that has given us the ability to design some very complex structures for fire. But I think Professor Andy Buchanan probably said it best when he talked about having a consistent level of crudeness. So we've developed all this great knowledge about how structures behave in fire, but we're still just using the standard fire to represent the fire hazard. Now, when we're looking at designing a structure for fire, obviously the fire is the single biggest constraint. It's the major input. So any of our conclusions about how the structure is going to perform are purely based on and limited by the assumptions we make about the design fire. And so we need to develop that knowledge. And so a fire, as you're all going to be very familiar with, is a function of the space that it occupies. And I think what Sean captured really nicely in his presentation is that these spaces are changing radically. When we started doing fire research in the 1900s, the rooms and the spaces that we were testing are very different. So the acoustic design of buildings and the building physics design is becoming much, much better. You can have an open plan 8,000 square meter office, and acoustically that works. So is fire safety going to be the barrier to people building those sorts of things? We've got much, much, much bigger spaces. We've got very highly insulating facades. So not only does that pose a risk in terms of fire spread within the building, but how is that going to affect the fire growth? So the growth rates that we're assuming for a structural analysis, is that actually the same? And I think we'll find that they're actually quite different. So this obviously is the major input then to our structural fire analysis. So all of this is going to change the way fires behave, and we need to be able to quantify that. So the two challenges we have are about identifying what kind of fire we might have in the building. Is it going to be more like a parametric fire, a travelling fire, an external fire? And then also, crucially, how severe a fire we need to pick. And that's probably one of the big challenges for design fires and structural analysis. So in my presentation today, I'm going to talk about just generally about building fire behaviour and what tools we have as structural fire engineers to characterise that. And then talking about fire severity, how we choose those design fires. And then just a tiny bit about structural response. So we're mostly talking about fire today. So you're all probably very aware of how fires behave, but when we're thinking about it from the structural fire point of view or any point, really we've got 4 principal parameters. So how much fuel we got, what's the ventilation, the volume and shape of the space, and then how insulating our boundaries are as well. So if we look at the traditional model, we've got very small, kind of medium-sized compartments, things that are no bigger than, say, maybe 150 square meters. And these are really well understood, relatively, fires. So we've got lots and lots of data about how these burn. We know how we vary the ventilation, how that will affect it. So we do know that we'll get variation of temperatures within the room, but these aren't really significant for a structure. So if a fire is changing and evolving in matters of seconds and minutes, the structure is much, much slower than that. So if the temperature starts to vary by a few hundred degrees over the course of like a few minutes or a few seconds, your steel or concrete structure is just too slow. It's not seeing that variation. So we're able to use a very simplifying assumption of saying we've got a single temperature within the compartment, and that's reasonable. And we know how we vary the fuel, the ventilation, and the geometry. We have lots of tools to calculate how that changes the growth rate and the duration of the fire. And there's probably some questions around how we determine what those are actually going to be for our building. So these models have been developing for a while. We have parametric fires now within the Eurocode, but they're obviously a function of the person who's created them. So the fuel load, we probably have quite reasonably good data about what kind of fuel loads we have in our buildings. But how do we define the ventilation? So how do we know? When you see people presenting their different parametric fires, they're making assumptions about how much window breakage they're going to have. If we've got a triple glazed facade, how confident are we about how long modern glazing is actually going to last in a fire? So, and we know that ventilation is one of the most, it's most sensitive to that parameter. So it's actually very difficult as an engineer, and there isn't really any guidance saying you should consider this amount of breakage. So it's very complicated, and people sort of wrap themselves up in knots over that. And these have all been validated in test compartments up to 150 square meters. And if you look in the Eurocode, there is a limit on using this. So you can't have a story height of more than 4 meters and an area of 500 square meters. In the UK, we say that we can ignore that. So we have a national annex to the Eurocode that says you can just ignore that 500 square meters and use this in compartments 1,500 square meters. And that's just not physically possible for you to have. These models were never developed to represent those fires. So we know that's not the case. And so as ARUP, we have a policy of not applying those to those areas. Unfortunately, nobody ever lets us burn 1,100 or 150 square meter fire compartments, so we don't have a lot of test data for that. So still thinking about flashover compartments, we've got flame projection. So a lot of structures like to express the structure, so they want it on the external of the building. And this is kind of harking back to the Pompidou. And so when Margaret Law developed her method for the Pompidou, she based it purely on the physics, the compartment fire dynamics. So we actually still use that method today because the physics haven't really changed. It probably does need to be tweaked, but we can actually make some reasonably accurate predictions of what the flame projections are going to be for a fire within a compartment. So when we get to open plan compartments, and this is what in ARUP we deal with a lot of this in terms of commercial buildings. We've got very large open plan floors. Tenants in buildings want interconnected floors. They don't want any separation between them. So we've got this idea of creating vertical villages where you'll have a couple of floors within a multi-story building, and those will all be completely open to each other. And acoustically they can make this work, and from a building comfort level they can make this work, but how's that going to happen in a fire? We've clearly got a risk of multi-story fires. And so what... and this probably really wasn't a surprise to people, but after the World Trade Center, it was kind of, I guess, helped by the forensic analyses that were done about what we call, but I'm sure there's lots of different terms for it, travelling fires. So we've got a really large floor plate. What you're more likely to get is just areas burning. So you'll have a patch of the floor that's on fire, and then that moves around the floor plate, and that's dictated by where the fuel is and how much ventilation it's getting. Now, from a structural fire point of view, these had always been ignored. So everyone knew that that's probably what would kind of happen if you had a really big compartment. But the thought was, well, the temperatures are going to be much lower, so clearly the standard fire and a parametric fire are much more severe for the structure. So as long as we're designing to those, we're safe. What we saw with World Trade Centers and other large building fires is that these fires can go on for hours, like 10, 14 hours. And so all of a sudden people started to think, well, actually, maybe they can be. That's a lot of preheating to put into your structure. And one thing we know about, for example, with concrete structures is that they're much more susceptible to kind of longer, slower fires where there's time basically for the concrete to heat up. So you actually get higher temperatures in the concrete structure in a longer, cooler fire. So these are kind of subtleties that start to come out when you're kind of have a better understanding of how the structure responds. So we at ARUP have actually funded some research into how we can go about characterizing this. So the way that fire is behaving is very complex. It's a complex fire dynamics problem. But when we think about it from the structural fire side, we're thinking, well, what are we worried about? We're worried about how long it might heat, is probably the main thing. So we developed a very simple model that used Alpert's correlation, where we have our near field, our burning area, and then we have our far field, so our smoke temperature is kind of remote from the fire. And we move this around the floor, basically, just to generate that preheating. Now, this is very early stage. There is lots more work that needs to be done in this field. It's a very simple model, but at least what it helps us to start do is get a grasp of how susceptible the structure is to this kind of heating. So if I've got, a few hours of kind of cool smoke temperatures, and that's still at 300-400 degrees, and then kind of a pulse of heating as the fire goes past that spot. And it requires a family of curves. You can't come up with one fire. I think that's the thing that we're sort of starting to move away from, is trying to define the fire. What we need to be designing our structure to is a family of fires and different types of heating, and kind of pushing it and pulling it to make sure that it's resisting all those different types of heating regimes. And so this is just a very kind of quick, that's how an example of how we would put that into a numerical analysis. It's very simple, but it's at least kind of making a start on how that can respond. And then we get into very large compartments, so transit halls, generally kind of in infrastructure types of facilities. And we know that here it's actually very difficult to generate flashover. We've got isolated fuel sources, and we've got very large space, so it's hard to create those conditions where you might get a flashover fire. But we also have very long-spanning structures, so we tend to want, if I was a structural engineer designing this, I would have to do a lot of robustness analysis, just to make sure that the risk of failure isn't going to be a risk for safety. And so we can do similar things with the fire. And so what we might end up doing is saying we don't actually need an awful lot of fire protection because the structure is remote from the fire, but locally to where we have a fire, then we can apply fire protection and make sure that it's not going to be vulnerable to that. So we know that, so this is just an overview of like localized fires. So you've got very high temperatures local to the structure, you've got radiation to the structure, so that's what we also need to look at. But the smoke temperatures tend to be much, much lower and not significant for the structure. And we have design tools within the Eurocode. There's quite a few correlations for kind of free burning fires, we would call them. And you simply, they're correlated to heat release rate, fire area and fire load. So that all sounds very simple, but then when you go to actually defining what it might be, if it's an arena, an entertainment arena, it's very difficult because they want it to be a very flexible space to actually define what the fire load is. And sometimes getting fire data for the kinds of things that you know are going to be in there. So if we were looking at a stadium, we might have those large projection screens. Not many people have burnt those, so we don't really know what the heat release data for those are. And we're trying to make estimates from things that we have burned, but generally people only let you burn old cars and all these sorts of things. So we need to think about that as well. And then combustible construction. So everything that I have just said is about non-combustible construction. So all of the data we have about parametric fires, about travelling fires, that's all based on structure that is not contributing to the potential fuel load for the fire. So for timber structures, I mean, we know we're able to define what these the charring rates are, but those are all based on furnace tests, and so how that would actually be replicated in a real building, nobody really is sure. And so, because we've always built, I guess, timber in lower rise construction, not that that's not still an issue, but perhaps for structural stability it's less critical. So when we get into tall buildings, your entire fire strategy is based around the fact that you can survive burnout. That's what we tend to use as our benchmark if we're doing a structural fire analysis. You need to be able to withstand the fire, and then the fire extinguishes, because the consequence of structural failure is so much higher. So there's a really big challenge for structural fire engineering, if we want to enable this type of tall construction, is how can we quantify the fire severity in a timber building? And so we're funding some research at Edinburgh University, but I know that it's something that's been studied kind of the world over, both in the US, Australia, everywhere where people are trying to build taller and taller. So those are the different types of fires that we can have. How do we choose our fire? How do we choose which one we're going to use? And how do we choose the severity? So as I've talked through the different methods, I've explained that there's quite a lot of user input and uncertainty that goes with those. And there isn't really a best practice guide on, if you're going to use a parametric fire, this is the amount of ventilation that you should use. So one consultant might produce a different parametric fire to another, and they have different fire severities. So what we're doing is you're not designing all the structures to a consistent standard. So that's a real challenge. So before just talking about that, I'll give you like a quick background to what we have in terms of prescriptive fire severity and what that means. So in the early 1900s, people wanted to know, well, how hot is a fire? So they ran a bunch of fire tests, and they said, okay, well, there's a reasonable kind of correlation. We know this is kind of roughly how hot a fire is, and so we have the ASTME curve, and that's pretty much the same, so we would call it the ISO curve, but it's effectively the same thing. And it's saying that in a compartment fire, you're about 900, 1100, 1200 degrees. Then we said, well, we need to set some performance requirements for the structure. So, okay, it should remain stable. It shouldn't let any heat and smoke pass through, and it shouldn't deflect too much because then it'll break our furnace, and we don't want to do that. So we set some goals. We tested it against a standard fire, and that was pretty much the state of the art in 1917. So that's how we designed our structures. And then Ingberg came along and said, well, not all fires are equal. So in a retail fire will be different to an office fire. And he surmised that that was because there was different amounts of fuel available in those spaces, which is absolutely true. So he did lots of surveys as to how much fuel were in these different buildings. And then he said, well, okay, now I need to equate that to our standard fire that we test everything to. So he would go to an office, figure out how much fuel there was, and calculate, so in this blue line, how big a fire that would be. And then to equate severity, he said, well, if I take the area under that curve and then the area under the standard fire, that'll probably be about equal severity. And so we know now that that's not true, but it was actually quite a kind of forward-thinking approach at the time. And what it also kind of set as the kind of benchmark. So if this is, if he's done his office fire and said, okay, well, that's about 60 minutes, is why our office and our prescriptive requirements now need 60 minutes fire resistance. So it all goes back to this work that was done. And so if you think about the performance that he was actually setting behind that is where we're saying you need to withstand burnout. That was the performance requirement. So that's what underpins our prescriptive requirements. So when we're thinking about a performance-based design, if we can design it to that burnout, then we will be demonstrating equivalence. So that's what we need to do with a structural fire engineering design. And so our goal is about withstanding burnout. The constraint is actually being able to define the fire reasonably well, and then we'll tell you how much fire resistance the structure needs in terms of minutes. And so that's kind of pretty much mid-century what we do. So how do we go about selecting that design fire? That's the kind of major input to the structural fire analysis. As I was saying, there's quite a bit of variation, and it becomes a very subjective decision that somebody needs to make about how severe to make a fire. And we can talk about engineering judgment all we want to, but we kind of want a consistent standard. So in the mid-2000s, they developed a code of practice in the UK called BS 9999. And what this tried to do was bring a fire safety things that we've learnt through fire safety engineering into a code of practice. So kind of formulate that in a code of practice. And it looked at the fire resistance periods and said, we need to revisit these because we know ventilation has a big effect. We know, kind of introducing suppression into the building reduces the likelihood of a severe fire. But how are we going to do that? And they came up with a risk-based methodology. They said, okay, we need to define what the acceptance criteria for design is. So how they did that was, he said, the risk should be constant for all different buildings. But the consequences of their failure are different. So if I have a single-story building, the consequences of that failing is very different to the Burj Khalifa, which is like nearly a kilometre tall, failing. But we control that risk by setting what the allowable failure rate is. So we're quite happy to let single-story sheds in the middle of nowhere collapse. We're not happy to let the Burj Khalifa or a nuclear power station collapse. And so that's how we go about controlling the risk. So for a very high consequence failure, we want a very low failure rate, and for a very low consequence failure, we can accept a high failure rate. And that gives us, more or less, a consistent level of risk across our buildings. And that's what you'll find in prescriptive design. Your single-story building might not need any fire resistance. Your tall building might need 2 hours, 3 hours fire resistance, depending on where you are in the world. And what the people who wrote BS 9999 did is they defined for the UK, because it will vary, because this risk level is about society accepting this risk. They defined what that risk level was for UK building stock. And so as a designer, if that risk has been designed, and I know the building that I'm designing, so I can work out what the consequences of the structural failure is, I can then work out what the allowable failure rate is. And that's what I'm going to use to choose the severity of my design fire. So when they did the work, they developed the methodology, and then they put some fire resistance periods in the code, and they adopted parametric fire curves explicitly into that. Now we know from what we've seen, what I've been talking about previously, that parametric fires are not always appropriate. We should also be including travelling fires. And this risk-based method, when we do it explicitly, lets us do that. So I'm just going to give you like a very quick explanation of how we do it. And we start off by saying, what are the inputs for our design fire? So we've got our geometry, fuel load, and fire size. So we can say, these are all the inputs, and then we create a probability distribution curve. So if I'm talking about ventilation, or fuel is probably a good example, because we've got lots of data on that, I can say, okay, the fuel load's going to be somewhere between X and Y, and then it'll probably vary in some fashion between the two. So if I've got, I think it's more likely that I've got the higher end of the fuel load range, then I can skew the results to that direction, or if I think we're more likely towards the low end of the range, I can skew them in the opposite direction. And so when I run through, I'll calculate maybe about 10,000 different design fires. And so for each of the inputs, I have some of these curves, and I just randomly sample them to produce kind of basically what you're trying to say is like all the possible design fires that you might have. So I get many thousands of design fires. And then for each of those design fires, I calculate what my maximum protected steel temperature is, because I'm trying to compare the severity. So it lets me rank the fires, basically. So one fire will only produce 300 in the structure, and then I might have some that's 600. And then I set what my acceptance criteria is. So what's your allowable failure rate? So I've got a graph that shows that a bit better. So this line is actually thousands and thousands of little dots. So these are all the temperatures. So I've basically ranked the severity of all my different fires. So I've got some very, very severe fires up at the end where I'm getting temperatures of about 1,000 degrees, even in a protected structure. And I can say, okay, well, what's my allowable failure rate? So if you look at kind of a less than 18 meter office building, you've got about 60 minutes fire resistance, and that's about an 80% performance. So we're saying the allowable failure rate is about 20%. So if I pick that as my design fire, what I'm effectively saying is I'm designing for all these fires in the blue area, and I'm discounting the fires in the red area as too severe for the structure. So if one of those fires occur, but they are very, very low likelihood to occur, then it is more severe than the structural fire protection is being designed for. But that it's still kind of in line with what our prescriptive requirements would provide. And so the taller my building gets, the higher that percentage gets. So when I'm up to 150 meters, I'm actually talking about 90%, 95%. And because of the shape of the curve, you're actually designing, if you go from 90 to 95, it's a very big increase in the fire severity. So that's how I choose my design fires. So I can zoom in. So if I zoom in on that line, what I've actually got is all these individual temperatures. Each one of them is a design fire. And so I can pull out those different design fires. And so in there, I've got parametric fires, I've got traveling fires, lots of different fire behavior. Now, they've all got the same severity. They all cause the same temperature in the structure. But we know, because of all the research we've done into structural fire behavior, that sometimes a traveling fire can be worse, sometimes a parametric fire. They do different things because of the different heating and cooling rates. So it's very important that we choose an envelope of fire behavior. So we need to look at different types of fires. And so just a few examples of that are, we know, again, in multi-story fires, so this comes back to the vertical villages that we were talking about before, that actually if we're looking at fire behavior under multi-floor fire, then that's very important. And what it's mostly important for is the perimeter columns. So where we've got a multi-floor fire, we can actually end up pulling in on those columns, and that can create a global collapse mechanism. When I'm looking at parametric fires, I need to look at like short hot and long cool, that's what we call them, because they elicit different. So a short hot fire is very fast. You get steep thermal gradients generated in the structure, and so you get lots of deflection because you've got lots of bowing. But if I look at a long cool fire, I get much higher temperatures generally overall. So I get lots of thermal expansion. So the structure's behaving differently under each one, and you cannot categorically say for all structures which one's worse. So we need to check both of them. And then when I look at my traveling fires, what I find is, and I've just compared here where we've done parametric fire calculations to our traveling fires, and what we're seeing is we get much bigger deflections under the traveling fires. And so that's important for when we're looking at how the slab is performing. If it's deflecting a lot, then we're very worried about how those strains are being balanced through the supports. So, in principle, what I'm saying is we need to have an envelope of behavior. So someone who comes with just a single design fire, I would generally treat with caution and say, well, have you thought about, how the variation in all your different input parameters will affect that design fire? Because you can't choose an absolute one. And so in conclusion, I think I'm reasonably on time. So I think our building structures and our fire hazard are, people talk about buildings becoming more complex, and I think they talk about it structurally, but actually they're becoming much more complex from a fire point of view as well. So we need to keep pace with that. And increasingly what we find through some of our performance-based designs is that there are things that prescriptive design would have missed. So it makes assumptions about how structures behave, but because the load paths that we're using are getting very complex, they weren't thought about when they were writing prescriptive design. Risk-based methods can be very useful in removing the subjectivity that goes into selecting design fires. And it creates a consistent standard, so we're all choosing design fires to achieve the same standard, and that's very important. Just generally, that we know that just because something has been fire engineered, it's still the same level of risk as if we designed it prescriptively. We use an envelope of design fires so that we can push and pull the structure in lots of different ways. And I think in terms of defining fire severity, one of the biggest challenges we have is quantifying for combustible construction. And I think that's a key thing that we need to do before we start kind of building at increasing heights in timber. So that's me.
Thank you.
Thank you.
Okay, thanks. Thanks,
Okay.
Susan.
Yeah, thanks. Yeah.
You can stay here.
Oh, no, I
you
can
got
stay.
some too.
Oh, okay.
No, thanks for your leading us into your conceptual approach about fire safety engineering. Misschien zijn er enkele vragen. Ik wil er gerust 2 vragen hebben tijd voor. Dus zijn er mensen die hierop willen reageren? Ja.
Great talk. Do you really want to get in line with the standard? If you know this much about the probability of failure, do you really want to get in line with the old requirements, which were basically in Burke in the end? Don't you want to go to a much lower percentage risk that a building collapse?
Yeah, we can. We can, as designers, we can define whatever that risk is. I think there's it's kind of an interesting one that you find yourself in as a fire safety engineer, because in the UK the law says your building remains stable for a reasonable period. And that leaves it very open to interpretation as to what a reasonable period is. So we use that concept of it should withstand burnout, and then we also look at, well, what were the codes intending to achieve, and so we will, try and provide something that's equivalent to that. It's very difficult to get building owners as well to think really properly about fire risk and what it means. I mean, it's a very rare client that wants something more than complies with the building regulations. So we would love to, but
Standard fire requirements
yeah.
are not in line with, I think, with the Eurocode probabilities of 10 minus 5 or something chance of collapse, which you presented like 80%. This was 80%.
Yeah.
Well, it's quite some fires where it goes wrong.
And that percentage gets kind of higher and higher as the consequence increases. And I think it's where fire safety engineering needs to go. I mean, if we look at structural engineering as a really good example, it's obviously a much older, there's been much more development. But all your safety factors that go into a structural design are all based on an implicit failure rate, and that's never really been defined for fire. And I think that would be a brilliant way for us to go, is to bring it into a risk-based sphere, so that it's explicit and everyone understands what that is. Yeah.
Okay. Yeah, one more.
You said for last compartment that you don't use the parametric fire curves. In the beginning you said something like that.
Yeah.
But you only showed the parametric fire curves in the presentation. So what
Those weird kind of things like that, were like the traveling fire, so the long kind of
ones.
peaks.
Yep.
But we will always run the parametric fires anyway, because so that the developer might sell the building as an open plan floor, but there will be subdivision. So we'll actually, when we calculate the parametric fires for doing that analysis, we don't do it on the basis of 1,000 square meters. We say, okay, well, it's been validated. So if they have a compartment that, or they create a room within that space that's 100, 150 square meters, then we'll calculate the parametric fire for that and test the structure under that. So you have to be aware of the fact that you're designing the building right now, but that's going to be there for 50, 100 years. So how are people going to change it? And nobody will think about doing anything to the structure ever again.
Okay, fine. One more last. This one. Okay.
Okay, thank you. Can you give us a short explanation about, I saw the building, the Twin Towers.
Mm-hmm.
You have a concrete construction with steel.
Yep.
What is happening there? It is so very fast turned down.
So there's, I guess, the work that we were involved in. So NIST did a forensic analysis that looked at plane impact and everything else. What we were interested in was the fire side of things. So the image that I had next to that was some of the analysis that we did, where we said if there was no plane impact, there was no damage to the structure, could you have created a collapse mechanism with a multi-story fire? So all our analyses just looked at the fact that you had 3, 4 stories on fire at once, and what we saw was a collapse mechanism. And that's because you've got, so all the floors are starting to pull in, and it creates a very large, so you've got your columns coming down, and your columns are basically being pulled in, and you've got a large P delta, and that's what then causes that global collapse mechanism. And so, but it's amazing how resistive people are to thinking about that. They say, no, your connections will have failed, blah, blah. You know, that could never happen. And I don't think that's true. You've got to understand what the upper bound is, like where your failure mechanisms can be. So that was the analysis that we did. But and I think that was kind of broadly agreed with kind of a lot of NIST's conclusions as well.
Okay. We conclude. Okay, thanks very much for sharing your knowledge. Thank you.
No
Thank you.
problem.
Oké, onze volgende spreker is